we said the first thing, since I forgot to do it, is going to be to go over this quiz. So this is for chapter 27. The exam is over 24, 26, and 27 because we come back to 25 on exam 3. All right, so first question was, what is EMF? Okay, the least logical is E. The next two more logical ones are B and D, just because for D, electromagnetic field, it at least matches up and it sounds reasonable, but it is not that. It's also not the force. Now, EMF at one time did stand for electromotive force, but we had talked about how that's not correct. It's not a force, it's actually work done by the battery per unit of charge that passes through the battery. So EMF, it doesn't stand for anything anymore because it stood for something that was not correct in the first place. So EMF is just what we call it still, but it's just EMF, doesn't stand for anything anymore. So to give a better sense of what it is, this was the thing about the escalator analogy for a battery. The height is the thing you ultimately want out of the escalator. You want to raise mass up, or in a battery, you want to raise charge up to a greater potential. The EMF is the thing the escalator does to make that happen. Or in the battery, it's the work the battery is doing to make that happen via chemical reactions. So there's a slight distinction between EMF, this thing we sometimes use this epsilon for, and voltage V. Another analogy for this, I mean, it's the same analogy really, is you are picking something up off the ground. You did work to set that thing up on the table. So you put in work. The end result of that is the height that the thing now has. It doesn't have your work in it. It has height, it has potential energy in it because of the work you did. So those are very closely related concepts, but they're not quite the same thing. The other reason there's a difference between them is because if you think about when you pick that thing up, not all of the energy you used actually went into lifting it. Some of it might have been internal kind of waste of like generating heat in your body, or some other things that did not specifically go into the height that this mug now has. Similar for batteries, not all of the work that they are doing on the charge actually goes into getting it to a higher potential. Some is wasted as heat, and that's why we talk about the internal resistance of the battery. And that's a good segue into the second one. Just to be clear, it's that first one, the work done per unit of charge. For the second one, real and ideal batteries. In ideal batteries, that's where we say these actually are equal. The work you put in over here equals the energy you get out, and both of these are on a per charge basis. The work you do per coulomb of charge that moves through the battery. That's EMF, work done per coulomb, per charge. And then the potential is the energy you end up with per coulomb of charge. So in a real battery, we are acknowledging that that's not actually true. You get out less than you put in because some is wasted as heat. And it is wasted inside of what we model as an internal resistance. Real battery does have internal resistance, while an ideal battery does not. There is no loss in an ideal battery. There is a difference between the two. In a real battery, the EMF is equal to the voltage. No, we just said that's true in an ideal battery. In a real battery, the EMF is higher, the voltage you get out is lower. It is choice B for this one. All right, number 3, around any closed loop in a circuit, the sum of the potential drops. So when we look through these, does it equal the current through the resistors? No, potential and current are two different quantities. They don't even have the same units, so those can't be equal to each other. Is the same for each loop in the circuit? No, I could give an example of that, like if we have like a 12-volt battery over here and a 6-volt battery over here, the potential rise in the first loop is 12 volts, and in the second loop is 6 volts. If in this case we're counting the other way, but you would count it at least as a contribution of potential to that loop. That means around the rest of the loop we have to lose 12 volts somehow. Or in this right loop we have to lose 6 volts somehow. So it doesn't have to be the same for each loop in the circuit. But it does have to equal the sum of the potential rises. So if we have drops across these resistors, they have to equal the rise provided by the battery. So if the battery provides 12 volts, we have to have a 12-volt drop across those two resistors. It does not have to equal the battery EMF because there could be, for instance, more than one battery. There could be other kinds of things producing an EMF. Lots of reasons it does not add up to necessarily 12 volts. It could be a different number if we've got more things going on in the circuit. And we don't use vector addition for this. That's why we like it, because it is much simpler than all the field stuff where you do need vector addition. Okay, a set of resistors is connected in parallel. What is the same for each? So in parallel is like this. This is the one that you can kind of imagine as if the battery is the escalator that lifts charge up. That charge has a choice of which resistor, which slide to slide down. But whichever one it chooses, it is going to go from the same initial height, the high potential point, to the same final height, the low potential point. It's how much charge chooses to take slide 1 versus slide 2 that can be different. So the analogy here is the voltage. That is what's the same, the difference in potential between the two sides. The actual physics reason for that is the what you call path independence of conservative forces. The electric force is a conservative force, and you may remember from physics 1, if I'm talking about the work done by, say, gravity, it doesn't actually matter what kind of trip I took to get from, say, a greater height to a lower height. I could have gone straight there. I could have done lots of weird curly-Q type motion, but the work done by gravity along either path is the same, and that's why the change in potential energy is the same no matter which path I took, right? I'm not expecting to, just because I walked a longer distance, have more potential energy where I ended up. It's the same deal here of consider these 2 points to be your 2 endpoints of your path. Whether I go this way or I go around this way, it shouldn't make a difference in terms of the energy that is available to the charge. So anyway, long-winded way of saying it's the voltage across each that is the same. The current can split because the charge coming in from the battery, it has a choice of whether it wants to go to the right or downward. And then it will eventually reconvene down here and join back together to return to the battery and start the cycle anew. So current can split. It's not the same. Voltage is the same across each. The energy dissipated by each resistor can be different because it depends not only on the voltage, but also on the current that is actually going through the resistor. If more current goes through one, it may dissipate more energy than the other. The resistance can be completely arbitrary different values. You've seen that in the lab. You can put whatever resistances you want in parallel. So it's not that. And it's not resistivity for essentially the same reason. You can pick materials of arbitrary resistivity to put as your 2 parallel resistors. And which statement about currents flowing into a junction is always true? So this is the junction rule. Let's see. Sum of currents entering a junction equals the total current from the battery. No, because you can have junctions that are not coming from the battery. So that'll do it. Something like this. There's more simple circuits that I'm sure I could draw to get the idea across, but this is what's coming to mind for some reason. So the battery sends out some current, it splits off, and already this current right here is going to be less than the current from the battery, but that's what's entering this junction. So if I sum up all the currents entering that junction, it's just that one because the other two I would expect to leave it. That doesn't add up to the battery current. So it's not that. Sum of currents entering a junction must be negative. No, I'm not even really sure how I would interpret that, to be honest. But then the sum of currents entering a junction must equal the sum of currents exiting. Yes, it is that one. What goes in must come out. And so if you see so ever many amps of current going into a junction. If half an amp, so let's say maybe an amp is going in, if half an amp comes out one side, half an amp better be coming out the other side, or else there's some charge that's gone missing somehow. And that is not what we see happen once the circuit reaches a steady state current flow. All right, the current entering a junction can't split into, that's what a junction is. It's a place where current does split into separate branches. And it's not the last one. Okay, that was maybe more detailed than the quiz recaps usually are, but are there questions on that?
I don't have a question on the quiz, but I have a question on the study, the practice exam.
Sure.
So on the practice exam for question, let me see, question 51. So like it looks like you're saying just because the current is split up into like a tiny resistor or
Mhm.
tiny area, uh, that just means it has like the smallest current passing through it. Is this true like all the time?
Maybe let me talk through this one a little bit more, and that may help answer the question better than if I try and give it an abstract sense.
Yeah.
So let's pick a certain amount of current to be leaving the battery. It's just going to depend on what resistances are connected, but let's say 10 amps leaves the battery. Well, I know based on the resistances that are given sort of how to infer this, but if I had different resistances, the answer could be different. So right here, the current has a choice, and the choice it's going to make is going to be based on the resistance it's seeing, quote unquote, from both branches. So if this is a really low resistance, and all of these add up to give a really large resistance, then more current will go through this branch than will go through the ones on the right. But on the flip side, if this one is a really high resistance and these all still add up to a really low resistance, then we will see more current go through the right branch. So there's nothing that guarantees just because more splitting happened that it's going to be less current if there's already tons of current going in through the right side.
Okay,
But
I get it now.
okay, yeah.
Yeah.
So yeah, it's not a general rule, and that's a good observation, a good question to ask. It is dependent on what resistances we're dealing with. So we had 20, 10, 30, and 60. And like I said here, the right branch in total is 30 ohms. And that's going to be a higher resistance, so less current automatically goes through that right branch than goes through the entirety of the 20 ohm resistor. And then it's another similar splitting through the 60 ohm down below.
Okay,
Yeah.
I get it now. Thank you.
Mm-hmm. All right, were there other questions off of the study guide? Also, this was me being kind of lazy. I didn't really want to do the whole worked out steps for it, but I think I did it in this next page.
Is number 18 going to be on the exam?
No. Were you hoping it would or would not?
Somebody I know didn't want it to be there.
Okay. It's we did, half a page on it, so it's really not fair to I don't like to do the thing where I pick that one obscure side note that I hope no one read and put it on an exam. So on that note, maybe let me pivot over to the notes and say what I do think is most important, unless there are other questions. Quick recap from 24 is it's very easy to forget what potential was in the first place by the time you're talking about circuits because you kind of just start to treat voltage as it's just a thing. Like you know it because you see it on a battery or you see it across a resistor from your voltmeter, but it stops kind of having any meaning beyond it's a number. So here's the reminder of what it stems from. Stems from this idea of potential. And I gave I think, better like hand wavy vibe description of electric fields than I necessarily did for potential. So let me try one here. So for electric fields, we called it like an aura that surrounds charged objects. A better way to put it is there's actually two kinds of aura around charged objects. There's one that has direction to it, a vector aura, and that's the electric field. There's a separate one that is tied to that. They're linked to each other, but it's a different way of thinking about it, and that's the scalar or number aura, and that would be the potential. So, an analogy that kind of gets across the idea of both is if you're talking about something that's really hot, it's radiating heat off of it. It's I don't know, like a out of an oven or something like that. You could talk one in terms of the actual direction of heat flow. So where is the heat going? That is a vector aura that the oven has because it has directionality. But you could also just talk about the temperature itself at different points around the oven. That's a scalar aura surrounding the oven, and that's like potential. So it's two different ways of describing the same thing, and they are related to each other. But what it really is the amount of energy that would be available to any test charge you placed around the thing. In this case, it might be what a thermometer would read around the oven at different points. It's that sort of idea. And you divide by the size of the test charge to again get something that really is just a property of the oven, not the thing you use to measure it. But in terms of this analogy we've been using, it's a more concrete one. You think of the field as like the slope of a hill and the potential as like the height of the hill. And of course, those are both related to each other as well. And the relationship is actually the exact same as the relationship between potential and electric field, which is what makes this a good analogy. I do think it's important to just internalize that analogy because it's the easiest way to answer conceptual questions. And I mean primarily, let me get down a few pages. Like once we introduce equipotentials and conservation of energy, I'm talking about questions like these first two. Where is the field strongest? Which way does it point? Where is the potential greatest or lowest? That feels very abstract unless you imagine the equipotentials as telling you different heights along a hill. And then this is really asking for the field, where's the hill steepest? And what direction is downhill? Which way does the field slope towards? And then for lowest or highest potential, just where is the highest point along that landscape and where's the lowest point? That's a much easier question to answer. But if you don't have that connection in your head yet, then they just feel like very abstract concepts. For calculation, really the first thing, if I look back through all of this, that I would have you calculate is the potential due to a group of point charges. So something like this, but more concrete, so with some numbers to work with. And the nice thing about this is that it's not vector addition like for electric fields. You just add these numbers together and that will give you the right answer. If you now remember that you do include or keep the sign of the charge. You don't do an absolute value for potential because these numbers and these signs are no longer encoding direction. They're just encoding, is it a positive or negative charge? You don't need to eliminate them to properly describe it. So that's the main calculation. And if I come back to here so we can mark some stuff out, the way we got to that is not very useful at the end of all this, but what potential is, conceptually is. So really this whole page is not relevant. This page is still good because it's starting to get at the idea of the analogy. And this page is, again, just to help you know what the analogy is saying. So I'm not testing on anything off of this page, but it hopefully helps get the idea of potential across. If I keep going, dipoles won't be on there. Equipotential properties are a good conceptual question. I like to ask about that a lot, but it is, again, just this hill analogy. If you can answer the top questions or things about the top thing, you actually already know how to answer them for the fields and potentials if you just remember the analogy between that and the hill. Conservation of energy is the other main calculation thing that happens in this chapter and could show up on an exam. So if I give you the speed of a charge at a certain point, what is it going to be at a different point? And you should be able to answer at least qualitatively before you ever calculate anything. If I say it's a positive charge and it goes downhill, meaning to lower potential, you should know it's going to be faster there. But if it were a negative charge doing the same thing, going towards lower potential, it is going to be slower at the lower potential because it is going downhill. They don't like to do that. Negative charges like to go uphill. They like to do the opposite of what positive charges like to do. Why is that? Well, what's making the downhill thing? Probably at the bottom of the hill is some kind of negative charge at the very low potential. It's what's making that low potential. And the negative charge that's rolling towards it doesn't want to. It's going to slow down as it gets closer to the big negative charge. The continuous charge distribution stuff is not on there. So we need to talk about it, but I'm really just going for like what's the real meat of the chapter, and it's just the individual charges and the potential they create. Okay, chapter 26. You don't need to know all these major differences between the static and moving charge. That's just to show you how different they are from each other. But here's where we actually define voltage for the first time. It's the difference in potential between 2 points. So you could think of that as, in the analogy, it's the actual height difference between 2 locations. Because really, in and of itself, height is not that important. You put a ball on top of a tall hill versus a shorter hill, as long as they have sort of the same change in height between 2 particular points, it's going to have the same effect on the ball. The ball doesn't care that it's doing this rolling at 100 feet above sea level versus 500 feet. It's more the shape of the hill that really determines what the ball's going to do. So height differences matter. Heights in and of themselves don't. Potential differences or voltages matter. Potential in and of itself it doesn't have a physical meaning until you give it a reference point. But this analogy is not even necessarily that helpful to remember at this stage. It's just to connect to the smaller scale local description of charge flow. So the current density, the electric field stuff, and resistivity, connect that to the large scale, which is the current, voltage, and resistance. So the main thing I typically ask about for this section is I might have you do a calculation similar to this one. How long did it take for the charge to move through a certain length of wire? And conceptually, it's things about the directions that charges are moving in wires. Because for the longest time, we thought it was positive charge moving up until we found out that it's actually negative charge moving in the wires. And so we've defined almost every physical quantity describing that motion wrong. But we've defined it wrong for close to 200 years, and it's kind of like we're in too deep now. We got to just stick with it and remember or force it to be as if it were positive charge. So let me come to the actual example, because this is where it really illustrates the issue. If we have negative charge moving upward in a wire, its drift velocity is the one thing that is actually kind of described correctly. We said, all right, we can't say its velocity is down if the electrons are moving up. That's too far. So instead, that is the one thing that agrees with the direction the charge is actually moving if it's negative. And all of the others are as if the charge were positive and it were moving the other way. So the electric field is in the direction of positive charge would feel a force in this wire. The current density is in the direction positive charge would flow if it were in the wire because of that electric field. And then current is the sum total of all those little current densities. You add all of them up. And so it also points in the direction positive charge would flow. If we were looking at positive charge flowing, then everything works the way it should. You don't need difference between the different kinds of velocities. But all of these equations that we derived, they all show up in this one example. So if the example makes sense, that's the main thing from that section. And then this example to get the direction stuff right. The other big thing in this chapter is resistance and what it depends on. So resistance is a property of a specific size and length of wire. Resistivity is a property of the material making up the wire. So resistivity is something that is intrinsic to copper or gold or silver. Resistance is because of that resistivity. If you mold a hunk of copper into a certain length and cross-section of wire, how does that resist the flow of charge? So it can be confusing what the difference is, but that's the difference. So they're related to each other through this right here. Resistance is resistivity, length, and area. And I usually tend to ask problems that connect that to this other way of talking about resistance, that it's voltage over current. So that's how we define resistance. You give the charge a known push by connecting maybe a certain battery, a 12-volt battery, and you measure how much charge flows. You measure the current. If you connect a 12-volt battery up to some wire and you see 6 amps of current flow, then by this definition, that wire and everything in that circuit has a resistance of 12 volts over 6 amps, or 2 ohms. So that's not Ohm's law. This equation is just one day we decided, you know what? I'm going to calculate resistance this way. I'm going to give this as a way to classify the resistance. Ohm's law is more specific. It says that that number doesn't typically change even if you crank up the voltage. If you add a second battery, now you've got 24 volts in your circuit, you're not going to see 6 amps continue to flow. You're going to see the 6 amps become 12 amps. Twice as much charge flows when you connect that second battery. And so the ratio of those two, 24 volts over 12 amps, it stays 2 ohms. That is not true in every material, though. So we distinguish and call the ones where that is true ohmic, and Ohm's law only applies to those. Imagine smashing these two questions together. That's kind of what I mean of the type of questions I tend to ask for this. So I might give you voltage and current and some of these properties about the wire, and I ask you to tell me how long is the wire, or how thick is the wire, or what resistivity does it have. You don't need to memorize or write down resistivity values. I would give them if they're needed, but I could ask you to calculate it based on the information given, for instance. Power I'm going to save for chapter 27 because when I ask you to calculate it, it's usually in the context of a circuit. So in 27, we had already talked about the distinction between EMF and potential. On the exam, they're, for all intents and purposes, the same thing, meaning all ideal batteries don't worry about internal resistance within a battery. And that means this first page, as far as the exam is concerned, is not that important. This page is like the why those equations work. But then if you're dealing specifically with series and parallel, I would honestly just jump straight to this question. If every part of this question makes sense and you feel like you could do it even if I happen to add another resistor, I usually actually go easier than one like this, but just if you feel like you can do it no matter how many resistors there are, then you're good on this. And the one bit of advice I have, if you're not as comfortable with that, is again, always redraw the circuit with each simplification you do, with each pair of resistors that you combine. Because if you don't, sometimes people try and mash every calculation of equivalent resistance all into one instead of doing this one by one thing. And inevitably, something tends to go wrong that way. And the problem is, if one thing goes wrong early on, everything kind of breaks down after that, and it's always hard to even decide how many points to give for that, but you get more typically if you just break it down step by step. As for that power piece I was talking about, I could ask, okay, how much power does a certain resistor dissipate? And that should be no problem, because if you do this whole analysis, you know the current and voltage for any resistor in the circuit and you just multiply them together. You're done. There are shortcuts and times when using one of the other equations, so I squared r or v squared over r could be faster, but you won't go wrong if you just do it this explicit way where you're going through everything and then you just multiply your current and voltage together. This is just to help you identify series and parallel. And then last thing, Kirchhoff's rules actually applying them. Again, if you have done this in circuits or some other course at some point and you feel comfortable doing it the way you did there, I acknowledge that that's a different way than we do it here. And that's okay. You're allowed to do it the way you learned in another course. I'm not testing on can you do it my way, I'm testing on can you do it. If you learned mesh analysis and do it with, subtracting off instead of saying it something equals something, do it that way. I think I'm smart enough to figure it out. The second point is I will not ask you to solve the equations you get. That does mean it's harder to tell if you got it right, because you can't tell if things look really funky. But I'm just going to ask you to get to right there. You do not have to find the currents. You just have to give me the 3 equations you need to find them. And I'm grading based on is stuff on the correct side of the equation, based on whatever method you're using. And I guess that's really it. That's what I'm grading on for that.
Would you prefer if we solved it all the way?
I won't be like, here's a bonus point for that or anything. If you want to do it in a calculator, if you have a quick way, like a matrix way to do it, sure, feel free, but I don't want you to get caught up trying to solve that system of 3 equations or feel like you have to, because it is going to take a little while and it's time that's spent on algebra rather than actually knowing physics,
Yeah, thank you.
Other questions on that?
So you said the partial derivatives were not going to be on the exam?
Right, yeah. So out of curiosity on that, what is it about those?
Oh, well, I'm in here with a lot of other people, and I just want to ask about that one. He doesn't like that.
Yeah, it's not on there, but you'll see this if you haven't yet in Calc 3. It's just a way to generalize the derivative to 3 dimensions, and it's honestly quantity that would make sense to ask about. Like, we don't live along a line in real life. We walk on hills and valleys. We walk in the park, and you stand on a bump. And so when you ask about the slope, like how steep is the hill, you have to account for, well, which way do you mean? Along, when I'm facing towards the north or the east or what? And that's what the gradient does. It accounts for the fact that there's 3-dimensionality to that surface rather than a 2D curve like you would look at in Calc 1. So Calc 3 is honestly the human version of Calc 1 in the sense of it's talking about 3D quantities. It's just harder because it's 2 extra dimensions.
I have a question. Could you go over work?
Work?
Yeah, the thing you're hovering over right now.
Where I say work is negative the change in potential energy like that?
Yeah.
Oh, okay, sure. So the example I always go back to is imagine you're picking up a ball. So when you lifted that ball up, what kind of work were you doing on it, positive or negative? If you're lifting upward and the ball moved upward, what kind of work is that?
Positive?
Positive. But at the same time, gravity was doing what kind of work?
Negative work.
Yeah, it's trying to slow you down, make it harder to pick the ball up. And as a result, it's sort of stealing the energy you're putting in. It's not completely throwing it away. Friction kind of does something more like that. It throws it away to the outside environment. Instead, what gravity does is it takes that energy you're trying to put in and stores it in potential energy. So as you pick that ball up, what happens to the gravitational potential energy within it?
That's it. Grow.
Yeah. And so the relationship between the work gravity does and the potential energy the ball gains is an inverse relationship. If gravity is doing negative work, it's because it's extracting energy out to store as potential energy, and so the potential energy goes up. That's why work is the negative of the change that you're seeing happen in the potential energy. And then in terms of potential, that's if you're, I guess, imagining picking up a bunch of little charges. You're doing work on all of them at once, or more abstractly, an electric field is doing that. Well, in that case, you might be more concerned about how much potential energy is available per charge. So maybe as a whole, the work you're doing, or the work gravity is doing, the work the electric field is doing, is 10 joules. But you've got a million little charges, and that might be X number of coulombs of charge. Well, per coulomb of charge, it's 10 joules divided by the number of charges that you have in your hand. So it's like a per charge way of describing how much energy they're getting. And that's more useful just because when we're talking about many different charges at once, you think more of a concentration of energy. How much is given to this amount of charge versus a different amount of charge. And that's the second piece. So you think of potential energy in terms of how much potential energy each charge has, the joules per coulomb. That's this part, the potential. And then how many charges are there? And that's the Q. Does that help get the idea across?
I think so. Thank you.
Let me do a quick scroll through the practice stuff, and I'll just see if I see ones and remember something that I'm not right now, because I don't think I'm firing on all cylinders at the moment. But if we look through, I guess I'm more looking for things where I'll say, like, why did I put that on this review? So far I'm seeing this is all pretty reasonable stuff. I guess I'll point out, I would lean towards simpler calculations of potential, so questions may look more like this and less like this one where I'm having to do some extra geometry to figure it out. And then this one, same deal. It's like asking a little bit more than what is total potential. So arrangements like this are more common. And then questions about conservation of energy in relation to that arrangement of charge you could expect to see. So I'd say I like this problem a lot. We said you don't need for rings and the gradient stuff. This kind of question I do ask sometimes on exams, and it gets people a surprising amount of the time. They'll be able to state Ohm's law no problem, but they don't realize I just tricked them into saying it's not true. So, I don't know. I guess just remember what it says. It says that changing voltage has no effect on resistance, even though the equation really feels like it should. And I think that's what messes people up, is they look at this. They say R equals V over I. And then they say, okay, voltage went up. Therefore, resistance went up. And I totally get that, but it's because you forgot that when voltage goes up, this goes up as well. The current goes up, and that means the ratio of the two did not change. That's the resistance. We saw the same issue with capacitance. It is an intrinsic property of the object that is resisting or holding charge. It's not due to what kind of charge you're trying to put on it, how much current you're trying to push through it. Is that 100% true? Still not really, because if you pump enough charge through a resistor or you put enough charge on a capacitor, it definitely starts to matter because it can make the capacitor explode or the resistor burn up. But for what you might think of as reasonable amounts, whatever the capacitor is rated for or the resistor is rated for, this is a correct behavior for it. Okay, yeah, questions like this is what I was talking about with using both V over I and the properties of the wire. And then again, if I'm asking for a power, I'm more asking in the context of, yeah, something like this question. Within a problem where you're analyzing a circuit, I then ask how much power is dissipated by this resistor within the circuit. And these questions are all just similar to each other. It's really just to give multiple ones to attempt. Any other questions, concerns? If not, I will see y'all on Tuesday. Feel free to email over the weekend if questions come up. But y'all have a good weekend.